A few days ago, Reddit user photo-josh took to r/askmath to ask for help on this geometry problem. It looks pretty elementary, a big isosceles triangle, a lot of given angles, and our goal is to find the missing angle x. Photo-josh was brave enough to mention that his wife, a math teacher, had sent him the problem, confessing her own difficulty in solving it. She believes there isn't enough data given to say for sure what x is, but instead it could be a range of answers. This admission, of course, guaranteed that many brave Redditors would profess how easy the problem is and call for the wife to lose her job. After all, if she doesn't even know that the sum of angles in a triangle is 180 degrees, then what on earth is she doing in a math classroom? And you won't be surprised that there were also many comments on her double CX. As for the problem though, many people on this post and on this strange follow-up post, which just asked the same question again to the same community, many people provided confident hogwash solutions. This guy filled in a bunch of the angles and eventually arrived at x equals 90, and Bumdorian says, oddly yours is correct, but mine is too with x equals 110, so it does in fact have multiple answers. Pizzy Strizzy comes in to piz on the parade. He says that's also incorrect. Just construct it with actual angles and measure it. You will see there is only one possible answer. Bumdorian assures us, nah, I checked it like 10 times. 110 works mathematically just as well. All the angles still add up. Here's another worked out answer. It looks like the conclusion here was x equals 60 degrees. This guy put together a self-proclaimed monstrosity and arrived at x equals 70 degrees, although later walks that back, saying it's not feasible. Well, that makes sense. Of course, the answer's not 70 because in fact the answer's actually 30, as confirmed by Owo human what the fuck? Well, I don't trust that guy. Apparently, the answer's actually 100. This guy simply gives up after what I have to assume was 15 minutes or more of back-of-the-envelope calculations. This guy says through trial and error, he concludes the answer is 80, and that the only way to find an actual answer is to physically measure the angles, because there isn't a single mathematical answer from the information given. This guy just got stuck. This guy got x equals 60. He did his work inside of a line. This guy says maybe he's wrong, and maybe he is, but I can't read it. Dirk Diggler here tells us that he arrived at an answer of 20 and it only took him 3 minutes. He says his solution, which isn't pictured here because this doesn't justify his claimed answer, but wherever his solution is, he says it's not nearly as pretty, but that's understandable since he did it in boxers. Abominable Fiance left a comment which added absolutely nothing to the discussion, but I'm glad they took the time to tell us that for them the problem is very easy. But despite its exceptional ease, they can't be bothered to provide any of the details. Of course, they were quickly informed it's not as easy as it seems, hence the edit. Never mind, it's not that easy, but I'm still lazy. One has to wonder what's the deal with all of these confidently given answers that may lack detailed solutions and disagree with all of these other answers. I've read hundreds of responses to this post and no one has shown their work. There have been lots of "it's so easy," "wife should quit," "the answer is insert arbitrary number," yet no one has shown their work. Why has no one answered the question and shown their work? To the credit of those who posted all these confidently incorrect answers, they pretty much all walked back their claims after realizing their mistakes. The great thing about math is you really don't have any other choice. It turns out this problem is not quite as easy as it would seem. So what's the deal? Does it really have infinitely many solutions? Or is the answer 20? Where does this problem even come from? I always love a good math problem with a story, and this one, it turns out, is a pretty well-known variation of a classic problem, sometimes called the hardest easy geometry problem, but better known as Langley's Adventitious angles. This is Edward Langley, and these are his adventitious angles. He published this problem in the Mathematical Gazette in 1922, The problem, of course, is given this isosceles triangle with the given angles, the goal is to find this angle x. The problem is harder than it looks, but the answer happens to be an integer number of degrees, which I'll not spoil for you. The problem prompted a lot of study, a lot of different solutions, and a lot of interesting variations. A standard variation of Langley's adventitious angles problem can be created by just changing these angles 20, 60, and 50 to some other integer triple, such as the 10, 70, 60 that we see in this Reddit problem. Note that in specifying the variation of the problem, we don't need to specify this angle, because the triangle has to be isosceles, so these two angles adding to 80 forces these two to add to 80. So if we say 10, 70, 60, this is forced to be 20 to preserve the isosceles triangle. Now, the reason for the wacky name, Langley's adventitious angles, is that among the 113,564 possibilities for those triplets of angles in specifying variations of the problem, only 53 of them, or roughly 5%, of 1% of all the variations yield an angle. We call this the derived angle since it's derived from the given information. Only 53 of the possible variations yield a derived angle with an integer number of degrees.
Adventitious.
Happening or carried on according to chance rather than design or inherent nature. And so these angles of Langley, which give a derived angle with an integer number of degrees, are certainly adventitious, for having such a derived angle is a rare thing indeed. So then, is the Reddit problem variation of Langley's problem an adventitious one? Does it yield a single integer answer for the derived angle x? Well, if you stop to look at some other people's attempted solutions, or tried the problem yourself by doing typical angle chasing, you'd find that just taking into account the angle sum of triangles and supplementary angles and all of that is not enough to pin down a single answer for x. However, in the given problem, there's more than just a few given angles and an isosceles triangle. The segments ED and BD have to intersect, and so there's only one possibility for x, which is the measure which forces this segment to coincide with this one. This segment, of course, has a fixed angle. These things can't vary, and so x can't either. But actually using these facts to derive the single correct answer for x is harder than it looks. But it can be solved just with basic geometry. In fact, there are several known solutions to this variation of Langley's adventitious angles. I'll walk you through one of these well-known solutions, and there are links in the description to sources with that solution and others, as well as further reading on this problem. For starters, I've traced out the problem as it was given in the Reddit post, just filling in a little bit of extra information and beginning the first step towards a solution. It was given in the post that these angles are 10, 70, 60, and 20. We then know, since the sum of the angles in a triangle add to 180, that this angle at C must be 20. So 20 plus 80 plus 80 is 180. Then we also know that angle AEB has a measure of 30 by looking at this triangle. 70 plus 80 is 150, so this remaining angle in that triangle has to be 30. Again, just by knowing that the angle sum in a triangle is 180 degrees, we can find a lot of missing information in this diagram. However, the problem is quite tricky, because to actually solve it and find this missing angle x, we do need to make a construction. Simple angle chasing is not enough. Our construction begins with this segment from D to a point we'll label F on the side CB, and this segment should be constructed so that it is parallel to AB. So we pick a point F on CB so that this segment from D to that point F is parallel to AB. Now, you should know, if we cut two sides of a triangle with a segment that's parallel to the other side, we create a smaller, similar triangle. That means, like the big triangle, whose base angles were 80 and thus it's isosceles, This smaller triangle also must have base angles of 80, and it too must be isosceles. Since we know that the base angles of this smaller triangle are both 80 degrees, we'll be able to figure out the measures of these two angles as well. Consider this triangle ADB. We certainly know the measure of this angle, angle ADB, because this is 80 degrees plus 60 degrees is 140. So looking at that triangle, this must be 40 degrees. But then this is a straight line, so these three angles must be supplementary. This one's 80, this one's 40, so this one must be 60 to bring the total to 180 as needed for a straight line. I don't want our diagram to get too cluttered with all this additional information, so I've printed out a new figure. This has some of the additional info that we now know. We know that this base angle of the smaller isosceles triangle must be 80 degrees. We also know, as we just discussed, that this angle here is 40 degrees and this one is 60. What remains over here is 80 degrees, but we're not going to label that. We also know over here, angle DFB is 100 since it needs to add to 80 to produce this straight line. So 180 total, this is 100. Next, we're going to get a pair of congruent triangles by constructing another segment. We're going to connect this point A to that point F. So draw this segment, and then we're going to look at two congruent triangles. Where the segment AF intersects this segment BD, we're going to label that point of intersection G. You can see there's some extra angle information here as well, which we will justify shortly. First, we assert a congruency between these two triangles. Triangle ADF is congruent to triangle BFD. There's triangle BFD. We know they're congruent by side angle side. They of course share this side DF. Then this angle is 100 degrees and this angle is 100 degrees. This angle we had already split up into 40 and 60, so certainly its total is 100 degrees. And this angle we previously established it's 100 degrees, although you see we can split it up further. But regardless, these two angles are congruent, both 100 degrees, and then these two sides are congruent. That's because the original triangle is isosceles. This big side is congruent to this big side, but then a part of it has been cut off when we look at these two segments. What's been cut off? Well, another isosceles triangle. This is congruent to this. So if we cut those congruent parts off of congruent wholes, what remains is a pair of congruent parts. So side, angle, side. The triangles are congruent. And from their congruence, we're able to conclude this angle here has a measure of 60 degrees. Because we already knew angle BDF had a measure of 60 degrees, but now from the congruence, this angle AFD must be the same. It must be 60 degrees as well. But then we have some equilateral triangles come into view. Triangle DGF, we've just shown that two of its angles have measures of 60 degrees. Hence, this third angle at that vertex G must have a measure of 60 as well, and hence it's equilateral. But if this angle has a measure of 60, then this vertical angle also has a measure of 60. It was given that this angle here is 60, so now triangle AGB, well, it must be equilateral as well with three 60-degree angles. Because we showed this is 60, we already knew this was 60, that forces this third angle to be 60, which means this little sliver that remains from the 70-degree total, 70 degrees is what we were given for this whole angle. This is 70 total, so if this is 60, this little sliver must be 10. So with this pair of equilateral triangles, we don't know that the triangles are congruent, we just know they're both equilateral. But certainly within each triangle, all of their sides must be congruent. Two other segments that we know are congruent now are FC and FA, because they're congruent sides from this big isosceles triangle. It's isosceles because it has this 20-degree angle, and since we just showed this little sliver has a measure of 10, we know that this angle total has a measure of 10 plus 10, or 20. So 20 degrees, 20 degrees. This triangle CAF is isosceles, hence segment FC is congruent to segment FA. So now in this new figure, I've highlighted that fact and constructed the final segment we need to bring this solution together, which is this segment from C to that point of intersection G. And this segment actually bisects the angle at C, so this part has a measure of 10 and this part has a measure of 10. And we know this segment CG bisects the angle because of the congruence of triangles CGA and CGB. And that's a result of side angle side. We know that GA and GB are congruent because we show this triangle that contains them is equilateral. We know that CA and CB are congruent because the original triangle is isosceles. And then of course both this angle and this angle, the one included between those congruent sides, both of those angles have a measure of 20 degrees. So by the congruence of the triangles, this angle is congruent to this one. Originally it was 20, so now it's 10 and 10. Now we're going to establish what is visually a slightly more awkward triangle congruence, that triangle ACG is congruent to triangle CAE. Here's triangle ACG and triangle CAE. And this congruence is a result of angle side angle. In triangle ACG, the angle at A has a measure of 20 degrees. Meanwhile, in triangle CAE, the angle at C has a measure of 20 degrees. So that's our first pair of congruent angles. Then, of course, the side CA is part of both triangles and, of course, is congruent to itself. And then in triangle ACG, the angle at C has a measure of 10 degrees. And in triangle CAE, the angle at A also has a measure of 10 degrees. So angle at A, angle at C, side AC, side CA, angle at C, angle at A. Thus, by angle side angle, those triangles are congruent. This, of course, means that their corresponding parts are congruent. In particular, that side AG is congruent to side CE. Thus, we have the following equation. Remember, we already showed that FA and FC are congruent. They're congruent sides in an isosceles triangle. So certainly, if we take away equal things from them, AG and CE, this is an equality. The significance of taking AG from FA is that this is FA, and if we take away AG, what remains is FG. Similarly, on the other side of the equation, FC minus CE, here's FC. If you take away CE, what remains is FE. So, in fact, this equation establishes that FG is congruent to FE. Then we previously showed that segment FG is congruent to segment FD because they're segments in an equilateral triangle. Of course, the drawing isn't even close to scale, which is part of what makes it difficult to solve. But if FG is congruent to FD, well then by this congruence, we know that FE is congruent to FD as well. We then know that this triangle, FED, is isosceles, because again, we just showed that two of its sides, FE and FD, are congruent. Of course, they don't look congruent in the picture, but the picture is not representative of the reality implied by the given information. Then finally, it's easy to finish the problem. Remember, the angle we're looking for is angle AED. So I'll write here angle AED. It's part of this isosceles triangle. We know that one angle of this triangle is 80, and we know that the other two angles are congruent because these are congruent sides, so their opposite angles must be congruent as well. This angle has a measure of 30 plus the unknown angle, AED, and so this angle must be the same thing. That is 30 plus the unknown angle AED. So we're going to take that and multiply it by 2 because there are two angles with this measure in that isosceles triangle. We're going to add that to the known angle, which is 80. And of course, this is the angle sum of a triangle, so it must equal 180. Subtract 80 from both sides and divide both sides by 2. 180 minus 80 is 100, divided by 2 is 50. So angle AED plus 30 must equal 50. Hence, indeed, the measure of the missing angle, angle AED, is 20. This is the so-called angle X in the Reddit problem. So wouldn't you know it, the guy who did the problem in 3 minutes in his boxers was right. X equals 20. Indeed, even if they look it, Langley's adventitious angles problems are not easy, and just because this solution worked for this variation doesn't mean it works for other adventitious variations of the problem. It is not a trivially easy piece of geometry, as all of the incorrect answers and people who got stuck make very clear. Indeed, I would say it's the requirement of needing these additional constructions to solve the problem that make the adventitious angles clearly not an exercise, but indeed a real problem. Let me know in the comments if you had any questions or perhaps some other interesting strategies for solutions to this variation of the adventitious angles. And consider joining Wrath of Math as a channel member for early and exclusive access to all sorts of fun videos, original music, lectures, and more. And be sure to subscribe for the swankiest math videos on the internet.
I'm unstable, I'm feeling hard to keep the cable cut and untuck the cable. If Texas Instruments don't reply, I think this time it might be fatal. Wish to sell my own fake, cause I'm jaded. Hate the odds that I calculated. Press and pull and pray and push it all the way through the whole blue planet faded. Psychosomatic habits, why you so